All right, so we're going to be starting 3-2 today. And we're going to be in 3-2 pretty much the rest of this week.
Never mind.
So it has a lot of graphing in it, and it's going to have some kind of weirdness going on. We're going to hit a whole lot of parent functions today, which you've seen before. You spent a whole lot of time in them in Algebra 2, but from like bunches of different chapters. So what we're going to start with is we're going to start with remembering lines and a couple of different ways to graph lines. I have two different forms up here. We also sometimes see stuff in standard form, not so much in this course. I'll put it up here as well. C equals AX plus BY. Like sometimes we'll see stuff in standard form like that. More often than not, we're going to see slope-intercept form, or this one is point-slope form. We may not have seen this one since Algebra 1. But these are the three most common forms of lines, and we are mostly going to see this guy and this guy. This is very, very similar to slope-intercept. It just uses any possible point that would be our x sub 1, y sub 1. And m is the same m as up here, where m is slope. We've seen slope-intercept form a lot more frequently. We're a lot more used to that one. And we're going to practice graphing these. We're going to be doing a bunch of graphs. So I've got these sets of 3. They're set up vertically, so if you want to glue them in your notebooks, you can just glue the whole strip in. There's also scissors in the boxes if you want to cut them apart. Totally fine. I'm going to put enough for everybody to have 2 on each set of tables because we're going to do more than 3 graphs today. We're going to go as many as we can. Gotta grab some more. I have tons. And I always have graphs. If you ever need graphs, I keep like this bin. This is full of graphs, either sheets or individuals. You're welcome to grab some. I also have pages that have sets of graphs in the bottom tray of paper over here. So I have tons of graphs. If you ever need graphs, you can have some. So we're going to graph these 2 lines, and I'm going to do both of them on the same graph just so that we don't take up that much space. Couple of graphs. So we have 2 equations down here at the bottom that we're going to graph. One is in slope-intercept form, one is in point-slope form. So this first one here, this is in our slope-intercept form. Minus 3x plus 2. Move this out of the way. So where do we start when we graph this? Our y-intercept of 2. The b is always our y-intercept. It's going to be the point 0, comma b, or 0, comma 2 in this place, or in this case. What's our slope?
3/1.
Careful. -3. It's a negative slope. So this is our m. How do I move with a slope of -3? Down 3 and 1 which direction? Somewhere is technically not wrong, but not particularly helpful. Rise over run, and we usually go to the right. Since it's negative, we need to flip 1. So we're going to go down and to the right. Down, 1, 2, 3, right 1. Down, 1, 2, 3, right 1. Or we could go up 3, 1, 2, 3, and left 1. Totally fine to do so. Still gives us a negative slope. We're going to connect them up. I do recommend when you're graphing to go all the way to the edges of the graph provided to you. My graph is a 10 by and yours is a 6 by on those, and that's okay. When you're graphing lines, please use a dang ruler or some sort of straight edge. I don't even care if it's a ruler or a folder or the edge of a notebook or the edge of your ID, which you're supposed to have with you. I don't necessarily recommend the edge of a phone because they oftentimes have buttons. If you ever need a ruler, I have bunches. Surfing Cat has bunches. We have rulers. They're supposed to be in the boxes, but somebody cleaned up my room last night and they were super ruffled. And we think it's one box. There's at least one here. We're not going to do tons with lines, but when we're working with lines, use a ruler. Oh, and I definitely did graph that one in blue.
You lose 20 points if you don't.
I'm just going to switch this to be blue.
One.
So our second equation over here is in our point slope form, which we probably have not seen in a couple years. So I'm going to do this one I'll do this one in black, just so they're very visibly different. So since we have our point slope form equation up here, we can kind of play match them up. Because we need to find the point that we're starting from and our slope. That's why it's called point slope form. Those two things are in there. So first things first, what's our slope going to be? 2. This guy's our slope. M. Watching our signs and being super careful. What is the point that is inside this equation? What is the x value of the point? Positive 2 and positive 3. So it's y minus the y value of the point, and in the parentheses, x minus the x value of the point. So we are starting at the point 2, 3, and moving with our slope of 2. How do I move with my slope of 2? Up to
To the right.
to the right. How many?
What? Because it's slope of 2, so it's 2 over 1.
Yep. Whole numbers have the invisible over 1. We don't typically write it. So up to over 1. Up to right 1. Up to right 1. Again, these are straight lines. We're going to use a ruler. The more dots you put, the easier it is to get your line to be straight. But when we're graphing lines, you need to use some sort of straight edge. It is not going to be a humongo thing we do. Like, we're not going to do tons and tons and tons of lines. But it will happen occasionally. Let me switch the blue one out to be something a little chunkier so we can see it a little clearer. Just making my blue line darker. Whenever we're graphing, I do recommend that you go all the way to the edge. It makes it a lot easier to see, a lot easier to read, all that jazz. Questions on lines? Because honestly, that's kind of what we're doing with lines right now. Okay, because we need to remember some other parent functions. Because we're going to deal with all kinds of functions in this chapter. So, we're going to think about quadratics and cubics and square roots. So our general forms for quadratics, cubics, and square roots are all up here. We have an a, our x with its exponent of some way, shape, or form, and then a plus k. We're going to graph first our parent functions. So my a is going to be 1. Like, there's nothing going to be there, and plus 0 on the end. So no transformations at all. So our quadratic parent function is going to be just our y equals x squared. That's what we're going to do for our quadratic parent function. You did these a lot in Algebra 2. We had like 2 whole chapters on quadratics. Lots and lots and lots. So we usually made tables, like a parent table, to plot up points to graph these things. I'm going to put mine over here just because you guys have a little bit more space and I don't want to have to make my screen that much smaller. So I'm going to put my table right here, where we pick x values to find our y values. What x values do we typically use for parent functions? 0, 1, and 2 for sure. But what did we forget to do? -1 and -2. We want that good view of the middle for most of these graphs. So we typically do things like -2, -1, 0, 1, and 2. Those are not the only options, but that gives you a really good view of the middle. And when we start looking at transformations, it gives us a really good idea of what happens to the graph. So if we're thinking about the equation y equals x squared, and my x is -2, what's my y? 4. For x being -1, what's my y? 1. If my x is 0, what's my y? My x is 1. And if my x is 2, 4. I heard a what? Where'd I lose us? Okay. Plot them up. We have -2, 4. Again, watch your scale. My scale's a little different. This is the old graphs, but I kind of like the ones with numbers better. -1, 1, 0, 0, 1, 1, 2, 4. Connect them up. Arrows on the ends. I'm gonna get that chunkier, just so it's easier to see. There we go. I like that better. That's easier to see. Vaguely familiar, hopefully. Hopefully vaguely familiar. We've seen parabolas before. We spent whole chapters on them. Cubics we may not have seen quite as frequently, but we should have seen them before as well. It's got a very similar parent function. Instead of being x squared, though, we're going to have y equals x cubed as our parent function. When we're working with stuff in a little bit, we're still going to have our a and k that do the same things here. And we're going to set this up with a table again and plot our points. So we're going to pick our x values, substitute them into the equation to find y values. So again, I'm going to use kind of the corner of my graph over here just because my graphs are gigantor on my screen and they take up a whole lot of space. So we pick our x values to find our y values. We just want that good view of the middle. So we're going to use, for our cubics, the exact same x's. -2, -1, 0, 1, and 2. Most parent functions use those 5 values. It's the good view of the middle. If my x is -2, what's my y going to be? Putting it through, my y equals x cubed. -8. -2 times -2 gives me a +4. Times -2 gives me a -8. How about -1? -1. How about 0? +1. +1. +2. +8. And I know your graphs only go to 6. You can put your dot just a little bit off. So plot up our points. -2, -8 for you guys to be just slightly off the graph. -1, -1. 0, 0, 1, 1, and 2, 8. So again, it's going to be just a little bit off your guys' graph. And we're going to connect our dots. It's going to make a little bit of a squiggle. It makes kind of an S shape when we do cubes. Questions on our cubes? Okay, so our last parent function we're going to look at today is our square roots. So we're going to use our basicest of basic equations, y equals the square root of x. Again, we're going to pick some x values to find y values. And what x's should we use? What do we think? When we're taking square roots, what do we want to use? Perfect squares. Do we want to use negatives when we're graphing? Why? Because they're imaginary. Do we know how to graph imaginary numbers at this point? Have you guys ever graphed an imaginary number? It's imaginary. It does not graph in the real plane. These are all real numbers. There's ways to do it, but that's a little bit more than what we do. Okay, so we're not going to use negatives, and since we're taking square roots, let's make our life easier and use perfect squares. So what perfect squares should we use? 0, 1, 4, 9. Just taking a few. You could go more, but very rarely am I going to give you a graph that goes any further than 10. I didn't even give you one that goes out far enough for 9 right now. It's like if you have a graph that goes out to 16, more power to you, but very rarely will I give you that. That's just a lot. So if I have an x of 0, what's my y going to be? 0. If I have an x of 1, what's my y going to be? If I have an x of 4, what's my y going to be? 2. If I have an x of 9, what's my y going to be? 3. So we're going to have our 0, 0, 1, 1, 4, 2. And then we'd have our 9, 3. It's going to look like this. So, and I know yours probably stops right about there. Hang on, let me get that with my chunky pen. I could always pick bigger x values for sure. Am I going to have an arrow on the left-hand side of this? Because if I go left, that's when I'm hitting my negatives and hitting my imaginary numbers. So square roots only get one arrow. So we are going to be playing with these 3 parent functions a bunch today. For the rest of the day, we're going to be playing with these and doing transformations on them. So questions on these before we start doing weird stuff with them. Okay, so before we start doing transformations, I'm going to remind us what the heck our transformations are. So I'm going to give you guys a second to write these down because you want to have them. So hot. This thing is so hot. It's so fluffy.
Oh, I remember doing this too.
Mm-hmm. Yeah, you've done all these. It's just been a minute. Okay. We ready for me to change it? There we go. So we're going to remember what our transformations are. And in that kind of general form, we had A and K. I also put H up here to remind us what it does. But we didn't even have it in our formula, but we may have it in our transformations. I don't remember. So A does a vertical stretch or compress. If A is farther away from 1, it's going to be a stretch. If it is between 1 and 0, it's a compress, because it's little. They're so cute, I just want to squish them. They're compressed. If A is negative, that's when we have our reflection over the x-axis. It is important that we are specific that it's over the x-axis. We will get into other reflections. So if you are one of those people that likes to write down the formal rules and how this works, it's our absolute value of A being greater than 1 is a stretch. The absolute value of A being less than 1 is a compress. And if A is negative, we have a reflection. So it's a stretch if our A is farther away from 0 than 1. It's a compress if it's closer to 0 than 1. And A being negative makes it flip upside down. H, when we're looking at our transformations, that would be inside our x that has a power. So we would have x minus h squared or cubed or square rooted. So it's inside that piece. And that would be our horizontal shift. H is horizontal. You know, we do the hula. H does the hula and goes side to side. K, that one was in our formulas. K is added on the end. K is our kangaroo or a kite. It just goes up and down. It's added on the end. It just goes up and down. And that's right there. K is a shift up or down. So our first one here that we're looking at here just has one piece. What kind of transformation does this have? A, H, or K? A. What is the value of our A here? A is -2. What does that tell us is going to happen transformation-wise? It's going to reflect the x-axis and stretch. Since A is negative, it reflects over our x-axis. And since the absolute value of -2 is bigger than 1, it's a stretch. When we do these transformations, there's lots of ways to build this. I tend to build it in a table like this, where I have my parent function in the middle, x plus y. So this would be the parent function we wrote on the last page, my -2, -1, 0, 1, and 2. This was our x squared, so we would have our 4, 1, 0, 1, 4. That's exactly what we wrote on the last page. This is my parent. Okay, I don't know why it's not letting me write an E. And then I do my transformations to the outside. You can do this however you want. If you want to do 2 separate tables, if you like to make one giant table, however you want to do it. Usually we take our x plus h and our y times a plus k. We apply our y transformations, so our reflect and our vertical, to the y, and we take our horizontal transformations and apply it to the h. So in this one, we don't have any h transformations, so my x's are just going to be exactly what they are. -1, 0, 1, and 2. I'm going to take my y's, these values in the table, and I'm going to multiply them by my a. So we're going to go times -2. So 4 times -2 is going to give me -8. 1 times -2 is -2. 0 times -2 is 0. 1 times -2 is -2. What in the chaos are you talking about? And -8. So we're doing that multiplication. We didn't have any k transformations. We didn't have any h transformations. So we don't need to do anything else with it. This is my new table. I just cover this up. I've got x's over here, y's over there. This is my point. Point, 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 point. Those same 5 points, I've just applied my transformation.
Is that using whiteboard?
What's up? Yeah, it's because it thought I touched the screen, even though I didn't actually touch the screen. My sleeve probably did, and it thinks it's flesh. So I'm going to plot up those blue points. X is on the left, my Y's are on the right. So -2, -8, which I know winds up off your graph because I only made you graphs up to 6. -1, -2, that one shows up on your graph. 0, 0, 1, -2, and 2, -8 is off the edge of your graph. When we connect these up, it has been stretched, so it looks like I took my parabola and stretched it and made it tall and skinny, and then flipped it. So it reflected across my x-axis, and it got skinnier. Tall and skinny. For our stretch, I always think of it as, it's a big kid now, it's big numbers, so it does yoga, it gets really tall and skinny. And when it's compressed, it's between 1 and 0, so it's little and so cute, and I want to squish it. Squish. So it goes. Okay, so first transformation, questions. We're going to do more. Like, this is what we're working with for the rest of the day. We're going to play transformation games. All right. Let's look at another one. This is a square root function. Ooh, I love it. It's not actually in my notes. Fun times. Where in the chaos did I get this from? Okay, works for me. All right, so this is using our square root function. So we are going to base it off of our square root table and apply our transformations in exactly the same way. What transformations do we have here? We have a stretch. Our A is 2, which tells us we have a vertical stretch by a factor of 2. And we have a K. This is a K, so we're going to have a shift up. It's a vertical shift. So we're going to take our parent table from where we wrote them on the very beginning for my square roots, because this is a square root right here. So my square root parent table, that's when we picked our perfect squares. So we would have our 0, 1, 4, and 9. Our square roots were our 0, 1, 2, and 3. That's our parent table. Parent. Then we're going to do our transformations to the outside. That's the way I do it. You don't have to. Again, you can do it in 2 separate tables, whatever you want to do. Graph the way your brain works. I'm going to take my x plus h. We don't have any h here, but I'm just going to write it down because it's great practice. And on our right-hand side, we take our y times a plus k. So we do not have any h transformations here. So my x's are going to be exactly what they were, 0, 1, 4, and 9. Then I need to take my y values times our a, so times 2 plus 1. So we're going to go times 2 plus 1. So if I take 0 times 2, what do we get? Plus 1. 1 times 2 plus 1. 2 times 2 plus 1. 3 times 2 plus 1. Woohoo! I ask such hard questions sometimes. Oh my God. All right, so that gives us our points. My two purple columns are my X and Y points. So plot them up. So we have our 0, 1, 1, 3, 4, 5, and I know it's off the edge of yours, but it's on mine. 9, 7. I could keep going this way, so we have an arrow on that end. If I go any further left, we're going to wind up in the imaginary numbers. So we do not put an arrow on the left-hand side of our square roots. But if we look at this compared to our parent function that we drew, it is definitely stretched. It is taller. And that end point has shifted up 1. The end point is an easy place to locate that. Okay. Questions on that one? Okay. So I have a couple I want to make sure we hit. There we go. I want to do this one for sure. So I'm trying to get my graph to move. There we go. All right. So let's do this one next. Then I'm going to throw a hard one at you. We're going to do at least 2 more, maybe a third if we have time. Yes, dear. Absolutely. I always have more graphs, and I have a whole set of sheets I haven't printed out yet. Need more graphs? Always grab us more. Did you guys graphs? I will grab more. I'm getting into the 10 buys. More graphs.
We love graphs.
These are 10 buys.
Yeah. If I sell it, I'll pay 5,000 Robux. And that's the cheapest.
How many less expectations on this one?
So that has 100 Robux.
Okay.
And now it's 5,000.
So we need to look at this and identify
That's amazing.
what our transformations are. Make sure we grab the correct parent table and apply them. So what are our transformations here? It's going to compress because our A value is less than 1. What else is going to happen? It's going to shift up 3
Yes.
because that's a K.
Yes.
So we're using our quadratic parent table here. So that's our x squared. So that's when we have our -2, -1, 0, 1, and 2. This is our x squared parent table of 4, 1, 0, 1, 4. Doing our transformations to the outside, we do our x plus h, which we don't have any h right now. And on this side, I'm going to do my y times a plus k. So we're going to go times 1/2 plus 3. So these guys stay the same. You don't have to necessarily write these out if you don't need to. So if I take 4 times 1/2, what do we get?
5. 2.
Plus 3. 5. 1 times 1/2. Plus 3. Yeah, and I don't care if we do this as a decimal or if we do it as a mixed number or if you do it as an improper fraction. Improper fraction is probably the hardest to graph. To do this as 7/2, it's not always easy to spot intuitively. But if that works for your brain, more power to you. Doesn't matter to me. So 0 times 1/2.
3.
0 times 1/2.
0, 3.
Plus 3 gives us 3. And then if we've set this up right, it should be exactly the same because parabolas have that line symmetry, where it's exactly the same on either side of our vertex. So plot up our points.
So, okay.
-2, 5, -1, 3.5, 0, 3, 1, 3.5, 2, 5. Okay, so we're usually not too bad on our quadratics. I'm gonna throw a hard one at us now. We do have time for it, I promise. It's hard, but it's not that hard. Like, we'll be okay. Ready? X equals 1/4 y squared. Why in the world would we do that? Oh my gosh, that's just me. So you could, it's a thought, but it's actually, that would only give us half of our graph if we did a square root. So we want to leave it how it is, but we notice how similar this is to something we do know, right? This is really, really similar to y equals x squared, right? But it's just that the x's and y's are switched. So if I take my parent table for y equals x squared, where we had our -2, -1, 0, 1, and 2, with our 4, 1, 0, 1, 4, same parent table we just used, and then I get x equals y squared, which is almost identical except my x's and y's change places. So take my two columns, switch them. So my x's are what was in my y column. These guys. 4, 1, 0, 1, 4. And what was my x's becomes my new y. -2, -1, 0, 1, 4. Now we have to apply our transformation. What transformation do we have here? What's up? Say that again. We notice how similar this is to a quadratic, right? Y equals x squared. The only thing that's different is my x and y's change places. So I took the normal y equals x squared, and I made my x and y's trade places. So what was in my x's is now my y's. What was in my y's is now in my x's. Oh, I did put a 4 instead of a 2. I will fix that. What do we do for our transformation? Compress. We're going to multiply our y's by 1/4. So we're going to take our x's. That'll be our 4. We've got 3 minutes. Chill. 4, 1, 0, 1, 4. And our y's, we're timesing by 1/4. Because that's our A transformation. So what is -2 times 1/4? -1/2. What is -1 times 1/4? -1/4, or -0.25. 0 times 1/4. 1 times 1/4. And 2 times 1/4. 1/2. So my x of 4 has a y of -1/2. -2 times 1/4. We multiplied this guy by our 1/4. I did my transformations different over here. This is my y times a plus k. I put it over here. So my x of 1, we have -1/4, which is even closer. 0, 0, 1 1/4, and 4 1/2. When we connect up and x equals y squared, we get a sideways parabola.
Oh, it makes sense. Because it's in the y.
Because it's switched from our y equals x squared to sideways. X equals y squared. So that's why we didn't want to do it as a square root. We would miss that bottom half. It's not a function, it's ucky, but it's a thing. We will keep working in section 3-2 the rest of this week. So homework 3-2 is not due until Monday. Monday. What's up?